Okay, so define and find the limits of functions. So, unsurprisingly, the first thing we're going to ask you is, well, good, what's a limit? So, easy definition to run with. A limit is what value a function approaches. Now, in and of itself, that's probably not particularly useful to you, but we'll go through it and then we'll all make sense. So, we've got a couple of different functions here. We're going to go left to right eventually. Cool. Function 2x minus 4. Hopefully we can draw that by now, because if we can't, we're really in trouble. Brilliant. So I've got this. Okay. What I want to start talking about is, okay, what does this function approach if, let's say, x is 3? So, okay, we'll say 3 is going to be back here somewhere. So we got this. Okay. So where am I ending up? Well, alright. If I just put 3 into this, 2 by 3, 6 minus 4 gives me 2, I'd get 2. And literally, we can stop there for this. It's a super simple example of it, to the point of being boring. But we've got to start small before we can run. So, okay, how do we describe this in math language? What we're saying is, the limit as x goes to 3 of the function 2x minus 4, right? And then we've just said, okay, I'm making this x go to 3. What happens? Well, I can just put 3 straight in. So 2 by 3 minus 4. Cool, that turns out to be 2. Okay, fine. Well, that's nice and boring. Well, we can do any other number of values that we see fit. Just for argument, let's say limit as x approaches 1. Alright, what's that talking about? Oh, that just means, okay, let x go to 1. Where does this function get closer and closer to as x gets closer and closer to 1? Alright, well, we've got 1 in there. I'm going to end up there. Where is this? Well, I know how to get that by just chucking it straight in the rule. So the limit as x approaches 1 of 2x minus 4 is, well, okay, 2x minus 4 with a 1 in there gives me negative 2. Beautiful, easy, boring. Great. Boring's good because it's a nice easy place to start. Okay, well maybe this is a bit fiddlier with some more complicated function, so quadratic, hopefully we know how to draw this by now. Cool, well, limit as x approaches, let's say 1, just for simplicity. Cool, okay. Where's that talking about? Well, 1's way off here somewhere. Well, I could draw this and try to figure it out, but that's going to get really irritating really fast. So instead, I'm just going to chuck it straight in. 1, 4, 3 gives 8, and done. Cool. Similar story, we can go down here and just put in whatever number we want. Are there any numbers that I can't put in this and get some meaningful result? Well, no, this thing has a domain of all real numbers, so I could put anything in there and I'll always get some meaningful result. Okay, well, that's nice. It looks like no matter what we do, we can just plug this thing in, so why is this so fancy and annoying? Well, let's try something like 1 on x. Alright, so we'll start with exactly that again. 1 on x. Okay, what's that saying? When x approaches 1, which is up here. Cool, where am I approaching? Alright, well, 1 over 1, that gives me 1. Oh, actually, I should have been doing that in blue. To say the black bit is the question, the blue bit is our answer. Cool, alright, so yeah, put in 1, I still get a meaningful result there. Alright, well, what happens if we say something like x goes to 0? You go, oh, okay, well that's 1 divided by 0. Oops, 1 divided by 0, which is a bit of a problem. Because we already know that's not defined. Now, does that necessarily mean that we have no idea what this thing goes to? Well, not necessarily. We're going to add in a new little trick to this. A limit can exist. Yeah, a limit can exist potentially. What we're going to do is say, okay, what happens as x goes to 0 from the positive side? Okay, well, that would mean thinking about x is approaching 0 from the positive side. So I'm coming closer and closer and closer to the y-axis. As I go closer and closer to the y-axis, what's my y value doing? I'm getting closer and closer, I'm going higher and higher and higher. So this thing ends up being positive infinity. Now granted, infinity is not a number, it's a concept, but what happens as x gets closer and closer to 0 from the positive side, it gets closer and closer to infinity. Cool. So this thing does have a limit for x approaching 0 from the positive side. What about limit as x approaches 0 from the negative side for 1 on x? Well, that's a good question. Well, I'm going to approach from this side now. I get closer and closer to 0 as I go to the right for x. What's y doing? It's going lower and lower and lower and lower and lower. Ends up going off to negative infinity. Okay, great. So does this help me with what happens to these as x approaches 0? Well, this one's telling me I go off to positive infinity. This one's telling me I go off to negative infinity. Well, how can I simultaneously be going to positive infinity and negative infinity? I'm not approaching any one value. So, in this case, because of these two, we say does not exist. The limit does not exist. Okay, so if something approaching from the left and the right agrees, that's fine. We can still say that it has a limit. It's approaching something. But if they disagree, then we say the limit does not exist. So as a counterpoint to this, let's say the limit as x approaches 0 for 1 on x squared. Okay, well, we know what that looks like. Something like that. Okay, what does this thing equal? Well, if we do it the naive way, we get 1 over 0 squared. Well, that's 1 over 0, undefined. That's not going to help me. So I have to do a bit more thinking. Okay, well, what's it approaching as I approach from the left? What's it approaching as I approach from the right? So, let's check it. Limit as x approaches 0 from the positive side. Limit as x approaches 0 from the negative side for 1 on x squared. 1 on x squared. Okay, approaching from the positive side. So I'm positive, I'm going closer and closer to x is 0, so I'm going this way. What's y doing? It's going up and up and up and up and up. This thing is positive infinity. Cool. What about this guy? Approach 0 from the negative side. Okay, going this way, what's y doing? It's going up and up and up and up and up. Well, that's positive infinity. That's supposed to be positive, not an x. Positive, there we go. Excuse me. Great. Well, what does that tell us? Well, this time, as we approach from the right and as we approach from the left, they agree. If they agree, if and only if they agree, then we can say, great, this thing does have a meaningful limit. Because you can think of this sort of as going off to infinity and then hitting infinity at 0 and then coming back down from infinity after 0. So it kind of makes sense to say, oh yeah, this thing is essentially going up to infinity and then coming back down. Now there's a whole lot of little technical errors with that, but for our purposes, that will work just fine. Cool, so sometimes you can do things in the super easy way. You just chuck in whatever value you're interested in, chuck it in, do you get a result? If yes, great, it's nice, boring. That's most functions. However, every so often you'll come across these sorts of functions. If the limits disagree with each other when you come from the left and from the right, if they disagree, your limit does not exist. If they agree, however, then your limit does exist. Well, that's nice. Excuse me. Let's have a look at something that's a bit less trivial. Oh, we've got something divided by something else. Okay, well, we may not know exactly what that looks like straight away. And that's fine. We can always deal with things that we don't know what they look like. Otherwise, things would be pretty boring. So, you may have already seen a way to shortcut this, but we'll get to that as we go. For now, I'm just going to say, alright, what happens as... Oops, what did limit? Limit as x approaches, let's pick something nice and easy, we'll pick 0. Cool, for this guy. I'll just put f of x to save me having to write it all out again. Okay, well, let's just try the mundane thing, throwing it in. Well, that'd give me 2 on top, that'd give me 6 on the bottom, so I end up with 1/3. Oh, great, so in this case, that works just fine. Always try that first, because if it works, brilliant, saves you a whole lot of more irritating thinking. However, what if this time we say, oh, alright, what's the limit as x approaches -2? Alright then, for this function. Okie dokie. Well, -2 plus 2, it's going to be a big fat 0. -2 squared gives me 4. -2 in here gives me -10, so 4 with -10 is -6. Plus 6 gives me 0. Oh dear. Well, that's a little bit of a problem. So now we're going to have to think a little bit more carefully. Well, I don't even know what this thing looks like necessarily. So I've got to be really careful here because I can't just look at my picture and go, oh, it's going up, yeah, no, they agree, or no, they disagree, whatever else have you. So now we've got to think, how much algebra do I know? Well, let's think about this for a second. I've got x plus 2 over some quadratic. Well, generally if we're given a quadratic and we want to do any work with it, a good protocol is to try and factorise it. Conveniently, 2 things at times 6, add to 5, 2 and 3. Cool. Now, you'll be tempted to say, oh great, these 2 will cancel, so I get this. And you'd be kind of right. There is a slight little thing that we've got to put on here, which is, cool, this will be the exact same as that, so long as x does not equal -2. Okay, great. Well, can we sketch this thing? Yeah, we can, because that's just hyperbola. Moved across to 3, so this is -3, x equals -3. There's also going to be an asymptote along here, y equals 0. Cool, and we get this curve going, yep, something like that. And we can solve for the y-intercept, well, it's a third, so why not? Done. Are there any x-intercepts? No, because we've got an asymptote at y equals 0. Cool, alright, so we've got this. Well, does this help us or not? Well, now we've got a picture of it, we can actually think this through a little bit better. What happens as x approaches 2? Well, I get the limit as x approaches -2 from the right side of this function, f of x. So, approach -2 from the positive side. So start on the right and approach -2. Wait, -2? Did I put that on the wrong thing? Oh, yes, okay. Right. So this is -2. Okay. Can I reach this point? Well, yeah, I can reach a point here. If I put -2 into this, 1 over -2 plus 3, that gives me 1, hopefully. Yeah. Okay, well that's good. But remember, what was that one? But remember, x can't actually equal -2 on this, right? Which is obvious because we ended up with a 0 over 0, right? So we shouldn't be able to get a normal result. It turns out that this looks exactly like 1 over x plus 3. However, when x is -2, you've just got this little void in there. So it exists everywhere except for -2. Okay, what happens as we do x approaching -2 from the negative side? Okie dokie. From the negative side, so from the left, go to -2. Well, that's okay, we go past -3, so now we're coming down here, and we get to there. Well, that's fine, that's still the same point. So that's still at 1. Cool. Alright, well, the limit from the right and the limit from the left agree. Well, then the limit still exists, so that's okay. So even though we got this crap result, it's like, well, actually, it turns out, from this, it equals 1. Cool. So it's possible to have them agreeing on infinities. It's possible to have them disagreeing on infinities. It's possible to have them agreeing on different values. It's possible to have them agreeing on just integer values or any real number values. It's also possible to have them disagreeing on integer values, which we'll get into. But there we go. We've got this thing approaches the point -2, 1. It never actually touches it though. There is a void there. So this is what limits are for. It's for dealing with these annoying little things where technically it's not on that line, but you can think of it as essentially being as close as you want to that as possible. Because if you put any other number in this, if you put in -1.99999 in for x, you'll get something that's just shy of 1. You'll get 0.9999-ish. And if you put in -2.00001, you'll end up with a value of 1.0001-ish. Cool. So essentially, this point kind of exists on there, but it doesn't exist on there. It's just getting closer and closer and closer. It's approaching. Cool. Alright, well, what if we've got some more irritating thing? Alright, well, again, I don't really want to draw this. You can if you want. What happens as x approaches 0? Alright, well, to do that, I've got to take... yeah, okay. So, I'm going to call these bits part green, part blue, and part purple. Okay. Well, what happens as that happens for x squared? Okay, well, that's just going to be able to go straight in for a 0. Okay, what happens as this goes for this? Well, that also goes to 0. Right? Okay, that's fine. Now, next bit, these two agree. So, from that, I can say the limit as x approaches 0 for this entire function, since it's centering on those zeros, is going to equal 0, because when I came from the left side function, it approached 0. When I came from the right side function, it also approached 0. So no matter which way I come from, I get the same result. I get a consistent result. So the limit for this piecewise function, as x approaches 0, is 0. Great. Well, what happens if we go limit as x approaches 1? Alright. Well, as I approach 1, I'm only dealing with these two functions. So what happens as x approaches 1, what does this function do? Well, that also goes to 1. Okie dokie. What happens as x approaches 1 for the purple part? Well, sub in 1, I get 2. And just to make things clear, we'll say from the negative side, from the positive side, from the negative side, from the positive side. Cool. Okay. So what happens in general as x approaches 1 for this piecewise function? Well, if I approach from the left, I approach 1, but if I approach from the right, I approach 2. Well, those are two totally different values. I can't say that it approaches 1.5 because I get closer and closer and closer to 1 and closer and closer and closer to 2. And then it just instantaneously teleports between. So there's no smooth transition between them. This thing does not exist. Right? They have to agree perfectly. 1 away, not good enough. 0.0001 away, not good enough. They have to perfectly agree. And that's limits. So remember, whenever you're taking limits, all you're doing is saying, what value does the function approach whenever I put in x approaches something? So x approaches something, what does the function do there? From the left and the right have to agree. Cool. So that is 7F, double check. Yes, 7F. It's a very short chapter. A whole lot of these basic functions will come up, but we've done those a million times by now. If you've got any problems, email as always. Best of luck.